If we take a look at question number one, it discusses two different charging methods, the first being conduction and the second being induction. So if we take a look at what's given, we're asked to explain how to charge a neutral metal sphere with a negatively charged metal sphere through the process of conduction. So I've drawn out a few diagrams to make it a little bit easier to see. Here I have my neutral and my negatively charged object. It's important to recognize that for conduction to occur, the two objects must have different charges to begin with. That's the main thing that differentiates conduction from other methods. The other methods, the two objects typically start with the same charge, neutral, and then charge one another through either induction or friction. But conduction, you have to have two different charges. When those objects are allowed to make contact, so long as they are conductors, meaning they're made of metal or some kind of material like that, the electrons will jump to the more positive option. In this case, the neutral sphere is more positive compared to the negative, so electrons will spread out and they will continue to jump over to the neutral object until they both end with the same charge. So when you're charging with conduction, the two things that are important to recognize is that the objects must start with different charges and they will end with the same charge. Because if they ever ended with different charges, that wouldn't be the end. Electrons would still have the ability or still desire to jump to the more positive option. So there only will stop being a more positive option when both objects possess the same charge. So please remember you must start with different charges, but you have to end with the same charge. When we're looking at B, which is charging through induction, in this case we are discussing charging a neutral sphere with a positively charged sphere through the process known as induction. Induction is generally like a 3 or 4-step process. It's the same whether it's a positively charged sphere using or a negatively charged, but I'll explain here in this case with a positively charged. It would just be reversed if you were to use a negatively charged rod. So the first step is going to be to bring that charged object near your neutral object so that you polarize it. Now in this case, this object is a positively charged sphere. It has more protons than electrons. So the electrons in the neutral sphere, as long as it's a conductor, will be able to move to the side that is closest to that positive charge. Because these electrons would like nothing more than to get to the positively charged object. They're being attracted to the positive charge. Once you've polarized that object, you don't bring these two and allow them to touch. If these two touched, since they would be differently charged objects, and then allowed to touch, that would be conduction. But in this case, we are never going to allow this positively charged sphere to make any contact with any other objects. If I do, however, bring another conductive pathway, another conductive object, whether it's your hand, whether it's another sphere, something like that, when those two make contact, the electrons from the hand in this case will jump to the neutral sphere because the electrons in the hand would also like to be near this positively charged object. So the electrons in both of these are going to rush to the right side to be as close as possible to the positive. Just like these electrons would not choose the neutral hand over the positively charged sphere, the electrons in the hand also would not choose the neutral hand over the positively charged sphere. So there will be a migration of electrons towards the positively charged sphere. This sphere, because it's polarized, will basically suck the electrons or some of the electrons from the hand into the sphere. All right, then you remove that conductive pathway. So you notice that this object now has more electrons. It only had 3 here. It now has 5 because some of the electrons from the hand jumped into the sphere to be as close as possible to the positively charged sphere. You break that contact, and now those electrons are not able to jump back. So then when you separate everything to a wide enough degree so that these are no longer polarizing, you will find that you now have a negatively charged object because the electrons from the hand jumped into the sphere. So with induction, you wind up with the opposite charge than whatever you began with. So to slide up here quickly, you began with a negative and a neutral for conduction. You ended with 2 negatives. Well, it's kind of the opposite down here. You start with a positively charged sphere, which leaves the original neutral sphere with a negative charge. For number 2, Teflon is being rubbed against amber. The fact that the two materials are being rubbed tells you right off the bat that must be charging by friction. It would be induction if you had some polarization. It would be conduction if they had two different charges to begin with. But the key here is that it's being rubbed against, and anytime you're rubbing anything, you're going to be generating some frictional forces, and therefore charging by friction makes the most sense. To look at question B, describe the charge on both the Teflon and the amber. Well, the Teflon will become negative and the amber will become positive. Now, we know this because we can figure out that Teflon has a higher affinity for electrons and amber has a lower affinity. Now, affinity just means like desire or ability to form bonds with electrons. So, Teflon can form stronger bonds, therefore, it will rip the electrons from the amber. Now, I know this because we can look at the triboelectric series. So, remember, we're talking about Teflon and amber. So, if I slide down to the triboelectric series, we've got Teflon and we've got amber. So amber is here and Teflon is down here. So Teflon is down on the bottom, which is the side that takes electrons easily. Amber is a little bit higher up, so it's closer to the side that gives electrons easily. So amber will give electrons easily to the Teflon, which will take them more easily. So the Teflon will be taking the electrons, therefore becoming more negative, and the amber will be giving them away, therefore it becomes positive. All right, so as we slide down to question C, a person touches the Teflon rod at several different locations along the length of the rod. What happens in terms of electrons and protons? Well, first, it's important to recognize that the rod itself, as we discussed up here, became negative. The hand is originally neutral. So first and foremost, we need to recognize that protons do not move, not now, not ever. Therefore, they won't go anywhere. But the electrons will always choose the more positive object when two differently charged objects come in contact with one another. So when these two touch, the electrons will jump from the more negative to the more positive. Therefore, they will leave the negatively charged rod and jump to the neutral hand. Not because the hand itself is positive, but because it is the more positive option. You can think of it less as the electrons actually attracting to the protons, and more as all these electrons repelling one another off of the rod. Now, it's important to just point out that the reason why we had to state that the person touches the Teflon rod at several different locations along the rod is that Teflon is an insulator. So if the hand simply touched right here, it would just take the electrons from here, but nothing could flow through the rod because that can only occur in a conductor. So just as a side note, the reason why it needed to be touched at several different locations had to do with the fact that in order for these electrons to be able to leave, the hand must come to the electrons because since it's an insulator, the electrons cannot move through the material to the hand. So when these two objects touch, the electrons will travel from the negatively charged rod to the neutral hand, as is always the case with conduction. And as stated just previously, it's charging by conduction, and I know this because two objects began with different initial charges, and they were then allowed to make contact. I didn't rub the hand against the rod. I didn't use the rod to polarize the hand and then touch the hand with something else. I quite, in a straightforward manner, took two objects with different charges and allowed them to make contact. That will always be conduction. Question 3 tends to throw a lot of students off when they first see it because they tend to overthink it. They tend to maybe not fully understand how an electroscope works. But regardless of whether they know that, if you're very careful with the wording of the question, it should give away the answer. Maybe it doesn't give away the reasoning, but it should give away the answer. And what's happening in each case here is a charged rod is being brought near, but not touching neutral electroscopes. Now, the important aspect here is that it is not touching. You have to recognize that if there is no contact being made at all, then no electrons can transfer. This rod is not touching the electroscope. You don't have another object coming in and touching the electroscope. You have no contact between any of these objects. If there's no contact at all, there's no pathway for electrons to transfer, and you cannot wind up with any charge whatsoever. So these all have to be zero because they were neutral to begin with and nothing made contact with the electroscope. So electrons cannot magically have just jumped through the air. So you have to first realize that because no contact at all with anything occurred, that they all have to have a charge of zero. But that still begs the question, how do these needles actually wind up moving if in fact there is no charge in these electroscopes? And that comes down to the fact that each of them is only polarized. So I've drawn kind of 4 diagrams down here. Now originally they were neutral. I've eliminated this section here because this whole circular section and the base is just to give support. So the actual electroscope is really this T-piece with this little needle here. So that's all metal, it's all conductive, which means electrons can travel wherever they would like. So if you look at A, originally while these electrons would have all been spread out throughout here, when you bring a positively charged rod near, the electrons will polarize and will travel to the top to be as close as possible to this positive rod. That leaves the top part with a negative charge, the bottom part of the positive charge. That means this bottom section becomes positive, and the needle also becomes positive because electrons from both will have traveled to the top. If both of these sections just kind of have their electrons flee, that leaves both of them positive, and that's why this needle will begin to move. Because while the overall charge on everything is still going to be neutral, 1, 2, 3, 4, 5 protons, 1, 2, 3, 4, 5 electrons, the bottom half acts as if it's positive, which is why these two will repel. Similar thing occurs in B, just to a different degree. The reason why the needle didn't move as far is the bottom just did not become as positively charged as over here. That would suggest that this rod itself probably has a weaker positive charge than this one, because this was able to suck up more electrons and polarize it to a higher degree, so you get a higher positive region down here. This one wasn't as capable, which means this rod itself is probably slightly lower in positive charge, but in both cases, they will suck those electrons up. And for C and D, it's the same explanation, just reversed. In the case of C, the electrons are pushed to the bottom, making the bottom half negative, which is why this needle repels. Same thing over here, however, not to the degree it occurred in C. The needle is a little bit lower, so in both cases it polarizes it so the bottom becomes negative, but this is probably a stronger negative charge than this is because it polarizes to a higher degree. But no contact whatsoever, there's no way electrons could have transferred to or away from the electroscope. So there are no other options except for all zero. This is just polarization, what you're seeing. If I were to remove these rods, you would find that those needles return because the electrons will then return to their normal distribution. When it comes to conductors and insulators, they're just types of materials. Some people want to say that conductors are like objects that can transfer electrons. While that is technically kind of true, a conductor is a material, it's not an actual object. So a conductor is a material that allows electrons to move freely within that material. That would be things like metals, gold, silver, copper, people, salt water or natural water that has some kind of minerals or some kind of natural salt content. These are all materials in which electrons can jump from atom to atom very easily, and therefore electrons can move wherever they like within this object. Whereas an insulator is a material that does not allow electrons to move freely. Things like cloth, rubber, plastic, like wood, paper, anything that is not going to allow electrons to just jump freely. And again, it's a material. So you can certainly have an insulator transfer some charge. The difference is if I touch a conductor myself, because the electrons all around that material are capable of getting to my hand, I will probably feel a bigger shock if I touch a charged conductor because all the electrons will rush to my hand no matter where I touch. Whereas an insulator, I tend to get smaller shocks because I only get electrons transferring from that small section I touch. I have to literally bring my hand to all the other sections. It's why you get worse shocks from things like metal doorknobs, car doors, and you don't necessarily get shocks as bad from like a plastic computer case or something like that. So it has to do with the material and how well it allows electrons to move or not necessarily whether the object allows electrons to transfer, because most objects can do that. But a conductor allows the electrons from all over to move wherever they want, leave the object, enter the object, and spread out, whereas insulators do not allow that. For 5, what I've done on the side here is I kind of took a look at the information that was given, and I've listed out on the side what each charge or charge possibility would be. I'll kind of walk through and explain what I added, why I added it, and why I removed certain things. So for 5A, we're told that A has a positive charge, so it's positive. Object A and B attract. Well, there are two things that will attract to a positive. A negative will attract, or a neutral could attract because it'll become polarized, and then the side which is closer, which would act as a negative side, would attract to the positive. So negative and neutral are two objects that will attract to a positive. B and C attract. Well, we have two options here, so I'm going to ignore neutral for right now. If B is in fact negative, there are two things that will attract to a negative, a positive and a neutral will also attract to a negative. So I add positive and neutral because these are two options that will both attract to a negative. Now, B could also be neutral, so now I'll ignore this for a second. If in fact B was neutral and B and C are attracting, well, what will attract to a neutral? A positive, which I already have, and a negative, so I need to add that. So what I wind up getting is with the negative, I need to have a positive and a neutral because those will attract to a negative. And to represent the possibility of a neutral, I need a positive and a negative. So I leave all three: positive, neutral, negative. I'll explain why this is gone in a second. When I get to C and D, I'm told that they repel. Well, that right off the bat tells me that C cannot be neutral because a neutral object is incapable of repelling anything. So that leaves positive and negative. So I simply say if C and D are repelling, well, if C is positive and D repels, it must be positive. But my other option is that if C is negative, what would repel that? Another negative. So I'm not saying that C could be positive, D could be negative, vice versa. I'm just saying there's a case where C could be positive, and therefore D would be positive. And there's a case where C could be negative, and therefore D must be negative. D and E repel. Well, positive, negative. What would repel a positive? Another positive. What would repel a negative? Another negative. I have to leave both since I don't know which one this is. And the same applies for E and F. If they repel, well, a positive would repel a positive. A negative would repel a negative. So if you look at what's left here, my answer for B would be a negative or neutral. C, D, E, and F would be positive or negative, which is what I've listed over here. When it comes to part B, I'm told that A has a negative charge. A and B repel. Well, if A is negative, there's only one option that will repel that, and that would be a negative. So B must be negative. B and C attract. There's two things that will attract to a negative. It would be a positive as well as a neutral. C and D attract. Well, two options. If C is positive, there are two things that would attract to it. That would be a negative as well as a neutral. So I'll include both. But C could also be neutral. And what will attract to neutral? A negative and a positive. So due to the positive, I have to include a negative and a neutral. Due to the neutral, I need a negative and a positive. So that leaves me with all three. The reason why I've crossed out neutral is when I move ahead, it says objects D and E repel. If D and E repel, D cannot be neutral because a neutral object is incapable of repelling anything. So that leaves me with negative and positive. And if D and E are repelling, well, a negative repels a negative and a positive repels a positive. If E and F attract, well, if E is negative, a positive will attract that. If E is positive, a negative will attract that. And I actually just realized now that I would also need a neutral here as well. So I did not, I forgot to add this, but you should also have a neutral here as well because a neutral will also attract either a positive or a negative. So answer F down here should be positive, negative, or neutral. So I apologize for missing the neutral here, but if E is negative or positive and E and F attract, that means that F could be anything. The positive to attract the negative to attract to the positive, or a neutral which would attract to anything, either of those. When it comes to number 6, we're given two metal spheres two metal spheres rest on insulated stands. So we have two metal spheres. These are insulators, so we don't worry about the electrons traveling to the ground. They're initially neutral and are touching one another. A third metal sphere, which is C, is given a positive charge and placed in the air but not touching. Before we get to the questions, it's important to realize that since this is positive, electrons will want to be close to it. So the electrons in A will rush to B and then to the right side of B to get near object C, and the electrons that were already in B will also travel over. Now there's still some electrons in A, but most of them will travel over here to B. So there's a migration from A to B because there's touching, and that's allowing them to get as close as possible to C. So the questions are as follows. What is the charge on sphere A at this time? Well, if electrons left A to get to B, that means it would now be positive. Therefore, B must be negative because the electrons left A and entered B to be close to C. And this last question here, is the magnitude, meaning the value of the charge on sphere A greater, less than, or equal to? Well, it's important to realize that every single electron that left A entered B. So whatever number of electrons A lost, B had to gain because there's nowhere else for them to go. So if they were both neutral and A became positive 1 coulomb, B must have become negative 1 coulomb. If A became positive 20 coulombs, B must have become negative 20 coulombs. So it's important to realize that due to the conservation of charge, they must both have equal and opposite charges, but the value itself must be the same. If one of them has more or less charge than the other, you have violated the law of conservation of charge. You've implied that A gave B 10 electrons and A somehow lost more or less than B gained. Doesn't make any sense. So if there were like 3 objects here, things might be a little bit different. But when there's only 2 objects, whatever electrons one object gains, the other loses. There's nowhere else they could have gone. So conservation of charge states that you must have an equal, albeit opposite charge on these two spheres. Now, before we move on to the next one, that leaves A positive, A positive, C positive, and B has a negative charge, which is important to understand when we travel down here. So B is then taken and it's slid over so that it touches and makes contact with C. The important thing is that if I take a negative object and I make contact with a positive object, those are two objects, different charges, and they are now making contact, so conduction will occur. And during conduction, electrons will travel from the more negative to the more positive object. So electrons will jump from B into C until they both end with the same charge, because conduction, you end with the same charge on each sphere. So what happens to sphere A and the charge on that? Absolutely nothing. You've broken contact, right? I already gave its electrons to B. By sliding B over, you've broken contact. There's nothing in contact with A that can add or remove electrons. So the charge on A does not change. C, however, becomes more negative because electrons will choose the more positive option, and sphere C will become more negative as B becomes less negative, and they will stop when they both end with the same negative charge. To look at the mathematical portion, you just have to remember conservation of charge states whatever one object loses, the other object gained. So here we have to be very careful in terms of what steps are being followed and what's being asked. So if we look at question 1, we have spheres A and B are brought into contact. As a result, how many coulombs of charge will be transferred between the spheres? You have to pay very careful attention to whether you're being asked about what transfers or what is being possessed, because those are two different things. As an analogy, if you had a certain amount of money and you lent some to a friend, how much you possess means how much you physically have on you at any one point. How much you transferred is how much you actually handed to somebody else. Those are different amounts. If you had $100 and you handed somebody 10, you possess 90, but you transferred 10. You just have to be very careful with what's being asked. So if A and B are brought in contact, the first thing we should figure out is what will they both end with? What charge will both of them possess at the end? So I have a positive 2 and a negative 4, and when I add those together, I have a total charge between them of negative 2, split evenly among the two objects since these are the two coming in contact, and each will end with negative 1 coulombs. But they are not asking me how many coulombs it will end with, how many coulombs it will possess. It's asking me how many coulombs were transferred. So I can look at A and say I started with positive 2. I ended with the negative 1 that we figured out, and that's a total of negative 3. So basically 3 coulombs of charge are going to transfer. I could have also looked at B. I chose A, but I could have looked at B. If I started at negative 4 and ended at negative 1, that would be a change of positive 3, because one object gains 3 coulombs of negative charge, and the other one loses 3 coulombs. So it doesn't matter which one you look at, but I need to realize that the transfer is not how much they end with, it's the difference between what they started with and what they ended with, which in this case is 3 coulombs. For B, they want to know how many extra electrons sphere B possesses after contact. Well, after contact, it literally ends with negative 1 coulomb. So I need to use our equation. The number of something times the value of one of those things will give you the total amount that you possess. They're asking for how many electrons, which is the number. I know the value on one electron is negative 1.6 times 10 to the negative 19th. And I know the total charge, and again, not that's transferred, that was up here, but that is possessed at the end is negative 1 coulombs. So when I plug all this in, I just divide both sides by the elementary charge, and negative 1 divided by that charge gives me 6.25 times 10 to the 18th electrons, also known as 6.25 billion electrons. That's an incredibly large number because 1 coulomb of charge is extremely large. That's like a lightning bolt. We come down and look at question C. It's saying that now, after this has occurred, sphere C is then allowed to touch the two spheres so that all 3 are in contact. As a result, how much will each sphere possess afterwards? Well, if we take a look, we're not just touching all 3 of these from the beginning. We know from this question that the first 2 ended with negative 1. So what's really happening is we're taking the 2 negative 1 charges, which are these 2 after they've redistributed to equilibrium. We're then bringing a negative 16 coulomb charge, allowing it to make contact, and then allowing that redistribution to occur again. So I have a negative 1 plus a negative 1 plus a negative 16, When these three are allowed to touch, that's a total of negative 18 coulombs, divided evenly among the three objects, gives each a charge of negative 6 coulombs. Now, this isn't asking me how much was transferred, this is asking me what it possesses, so that's why I'm simply figuring out how much each will possess after contact. Part D says how many electrons will be transferred to or from sphere A as a result of the interaction described above. Well, we know that each will end with negative 6, and we know that the transfer is the change. Well, originally, A had negative 1 before C was brought over, and it ends with negative 6. So I know that A went from negative 1 to negative 6, which is a change of negative 5, but they don't want to know how many coulombs transfer, they want to know how many electrons. So once I figured that negative 5 coulombs was the difference, is what was transferred, I then plug that back into my equation that I discussed up top. The number times the value of 1 electron will give me the 5 that were transferred. If I just simply rearrange this equation, I should find that 3.125 times 10 to the 19th electrons were transferred, which is the same as roughly 31.25 billion electrons, which is a very high number, but again, 5 coulombs is a large amount of charge. For number 2, we're told two things. We're given the actual charge on object B. We know that's 3 microcoulombs. But we're not given the actual charge for A. We're given how many more electrons than protons it actually possesses. So the first thing I need to do is figure out what charge object A possesses. All right, using our same equation that we've been dealing with, the number of electrons times the value of 1 will give me my total charge. So we're told the number of extra electrons is 3.75 times 10 to the 13th. We know the value of 1 electron is negative 1.6 times 10 to the negative 19th. If I multiply those two, I'll calculate my total charge, which I get to be negative 0.00006 coulombs, also known as negative 6 microcoulombs. This is the same as saying negative 6 times 10 to the negative 6th. So we'll commonly write this as microcoulombs. Once we have that value, calculating the electric force is just as simple as using Coulomb's law. So we're given K, which is 8.99 times 10 to the 9th. Charge 1, as we've calculated up top, you can either plug in negative 0.000006. I prefer negative 6 times 10 to the negative 6. It's the same thing. That's charge 1. Charge 2, we're told, is positive 3 microcoulombs, and I have to divide it by the 3 centimeters, which is converted to meters, squared. When I plug all of that in, I get negative 179.8 newtons. I hate the negative. We erase it. The negative simply tells me that these two are attracting one another. So if A is being attracted by B, that means A is being pulled to the right. So I erase the negative and I simply write 179.8 newtons directed to the right because that is the direction that B is pulling A. For C, I could certainly plug in the same exact numbers into the same exact equation and get the same exact value, or I could just recognize that that will give me the same value. I could also say that if A is being pulled on by B with 179.8 newtons, then Newton's third law tells me that A pulls on B with 179.8 newtons in the opposite direction. For every action, B pulls on A with this force, there's an equal and opposite reaction. A pulls on B with this force in the opposite direction. To find part D, we're told these two spheres, these two objects, are moved some new distance, and we're given that there's an electric force of 11.24 newtons. They'd like us to figure out how far apart the charges must be located. And you're going to quite simply, again, use Coulomb's law. However, we are going to use r for our unknown distance because we have everything else. Now we know that this is a negative and a positive charge from our calculation up here, and they will attract. So I made my force negative because in Coulomb's law, a negative force implies attraction. So I'm saying here there's an attractive force of 11.24 newtons. I've plugged in my K, my two charges, and my unknown distance squared. So the first step is to multiply both of these sides by r squared. That leaves me with negative 11.24 r squared equals these three values over here. I then divide both sides by negative 11.24. That leaves me with r squared equals, and this value right here I got by multiplying 8.99 times 10 to the 9th times my two charges and dividing by negative 11.24. So this entire side right here, it just resolves into 0.014, but that equals r squared. Take the square root of both sides, and you'll find that r equals 0.12 meters, also known as 12 centimeters. That's how far apart these two must be if that's the exact force that they are experiencing. For number 3, we're asked to find the net force on charge B as well as on charge C. The important thing to notice is that charge B is here, which means A is acting on it, and C is acting on it. So we have to look at those independently. First, I'll look at the force of A acting on B. I will just plug it into Coulomb's law, K times the Q for A, the Q for B, divided by the distance between them in meters squared, and that gets me 89.8 newtons. I say to myself, if A and B are positive, then A is going to repel B to the right, which is why I've added a rightward directed arrow. For the force of C acting on B, I plug in K, Q for B, Q for C, divided by the distance in meters between them squared, and I actually get a negative 226.55 newtons. Now again, the negative doesn't imply direction, it applies attraction. That means C is attracting B. That means B will be attracted to the right in terms of C, so the 226.55 is directed to the right. I will write a rightward directed arrow and erase the negative. Both of these arrows point to the right, therefore they go in the same direction. So the total force acting on B will be this rightward force added to this rightward force, which gives me a total of 316.45 newtons directed to the right. When it comes to charge C, I will do the same thing. I can use a shortcut here, though. I've already calculated the force of C acting on B as 226.55 newtons to the right. So Newton's third law tells us if C pulls on B with 226.55 newtons to the right, then B must pull on C with 226.55 newtons, however directed to the left, equal and opposite forces. If I were to plug all the same values in, I would still get negative 226.55, but I would say that B is attracting C, in this case, to the left, but I kind of like the Newton's third law explanation a bit better. Now, we have yet to calculate the force of A on C. We didn't do it up here, we didn't do it here, so I actually have to plug this into Coulomb's law because I have yet to look at that. K, Q for A, Q for C, and I have to add the 6 and the 5 because that's how far apart they are to get 11 centimeters, which is 0.11 meters. Square that. If I plug it into my calculator, I get negative 20.80. The negative means it's attractive. So if A is on the left and C is over here, that means A will attract C leftward. So I erase the negative and I replace it with a leftward pointing arrow. If I have two leftward directed forces, they're going in the same direction, so I add them. And the final answer would be 247.35 newtons directed to the left. Finally, with number 4, I already have these values from the previous problem. I know the force between A and B is 89.9, and I know the force between B and C is 226.55. Now it's possible to steal these numbers up top, the 89.9 and the 226.55, because I gave the same charges and the same distance between them. The only thing I have to recognize is that by changing these, the direction of some of them have changed. So while the 89.9 was originally directed to the right because A was repelling B to the right, well, we've changed the orientation. So A still repels B, but no longer to the right. A will be repelling B downwards. So the 89.9 should be directed down, and B is still being pulled towards C, so this should be unchanged. Now you have to follow the tail to tip method when making your right triangle for these problems, and there's two ways you can do it. I'll show you both, and either one are acceptable. I can draw the downward arrow first, which is my 89.9, and without picking up my pencil, I can then draw the rightward, which is 226.55, and then I can set up my hypotenuse and find my angle. Alternatively, you could start with your rightward force, the 226.55, and then the downward force, which is 89.9. You'll find the hypotenuse is the same, it's pointing in the same direction, you'll just get a slightly different angle. So in either case, I use Pythagorean theorem, a squared plus b squared equals c squared, and I will find that the force, the net force, when I combine these two, acting on B is 243.74 newtons. Now the two angles you could find would be whether you're referencing the x or the y-axis. So if you went down and to the right first, you want this angle where you started drawing your vectors. And I like inverse tangent here, so it's going to be the opposite over the adjacent. So the opposite is 226.55 over 89.9, and I will get that this is 68.36 degrees. Now this is being measured off of this vertical line, so this would be 68.36 degrees measured off of the y-axis. Whereas if we were over here and we reversed it, you still get the same hypotenuse, but you're actually measuring off of this horizontal vector, which is the x-axis. So 21.64 degrees off of the x, or 68.36 degrees off of the y, it gets you to the same exact point, and both of those answers are acceptable.